Okay, we're going to talk about the normal probability distribution. Make sure you read this first paragraph here on continuous random variables. Okay, here we see a histogram of a discrete probability distribution. The tick marks on the horizontal axis represent the values of the random variables, so 1 through 16. The heights are their probabilities. So actually each one, as you see, as you start from the beginning, you have low probabilities, and then as you get toward the middle, the probabilities tend to rise, and then as you move over this way, the probabilities drop. Now, the sum of all these probabilities will add up to 1, of course, but what's interesting here is you have a somewhat symmetrical picture here. That's if you connect those rectangles, you get sort of a bell-shaped curve, and this bell-shaped curve is called the normal curve. And this normal curve has some interesting properties. So let's talk about some of the properties of the normal probability function, or the normal curve. Well, the first thing I want to talk about, the curve is determined solely by its mean and standard deviation. Now, the mean will tell you the exact middle of the curve. So if the mean were, say, 100, then the curve would be centered about 100. The standard deviation tells you how wide the curve is. So this curve might have, kind of a median standard deviation. But if you had a curve, a skinny curve, that would have a small standard deviation, whereas if you had a very wide curve, that would be a large standard deviation. The curve is symmetrical about the vertical line, or the mean. So this vertical line that's right in the middle, let me show you down here. This vertical line that's right in the middle here is, the curve has symmetry about this line. So we have symmetry about that line. So in other words, half of the area under the curve is on this side, and half of the area under the curve is on that side. Now that brings me to an important point. The total area under this curve and above the x-axis is actually 1. So what that means is, on this side, then the area of the curve, so the area of the curve on this side is actually 0.5, and the area of the curve on the other side must be also 0.5, the area under the curve I'm talking about. Okay, but there's also some other interesting things about this curve. If you look here, right here, it says the area from one standard deviation to the left to one standard deviation to the right is about 0.683. So what that means is that if you take the area, say, from here, hang on, let me get a better picture of that. If you take the area, say, from here under the curve over to here under the curve, then that area in here under the curve is actually about 0.683. But if you take the area from 2 standard deviations to either side of the curve, then you're going to get an area of 0.954, which roughly is 0.95, but 0.954. And then if you go 3 standard deviations to the left over to 3 standard deviations to the right, then that's almost everything. That's basically everything under the curve, except just a tiny bit that's out here and a tiny bit that's out here. So, but we say that's 0.997 is that area. Now, when I say that's area, that's the same as probability. So the total area under the curve is 1, and the area between 3 standard deviations to either side of the mean is 0.997, or 99.7% of the area. from 2 standard deviations to either side of the mean, it's 0.95 or 95% of the area, and 3 standard deviations, 1 standard deviation to either side is 0.68 or 68%. Now these two are rounded to 2 decimals. Up here you can see if you go 3 decimals, it's 0.683 and 0.954. Okay, so that's the normal curve. So from this curve, we could answer some basic questions. Like if I said, let's say that we know something about the curve. Let's say that we know the mean is 80 and the standard deviation is 5. So if the mean is 80, 80 would correspond to the very middle of the curve. And then if the standard deviation is 5, then 85 would correspond to 1 standard deviation to the right, and 75 would correspond to 1 standard deviation to the left. 90 would correspond to 2 standard deviations to the right, and 70 to 2 standard deviations to the left. And then 95 would correspond to 3 standard deviations to the right, and 65 would correspond to 3 standard deviations to the left. So if we wanted the area of the curve that's between 70 and 90, then we're looking for the area from 2 standard deviations to the left to 2 standard deviations to the right. And that's given to be about 0.95 or 0.954. If you wanted to get the area between 80 and 85, well, that's from the mean to 1 standard deviation. Well, if you go 1 standard deviation to the left to 1 standard deviation to the right, you're going to get about 0.68. But since we're only doing half of that, 80 to 85, that area in here would only be half of that, which is 0.34. Now, if you wanted to get more complicated, let's say you wanted to go from 70 to 85, well, from 70 to 80, that would be half of 0.954, which is about 0.48. And then from 80 to 85 would be half of 0.68, which is 0.34. So the area under the curve from 70 to 85 would be the sum of those, which is about 0.82. Or if you, now this gets a little bit tricky, but if you wanted the area from 85 to 95, then basically you could say, well, the area to the right of 80 is 0.5. So all I need to get the area from 85 to 95 is, let's find the area from 80 to 95, okay, and that is half of 0.997. So let's say that's about 0.499, and then we can subtract from that, let's see, 0.34. The area from 80 to 85 is 0.34, so take that away from the area from 80 to 95, and that will give me the area from 85 to 95. So we have to use a little geometry there to figure it out. Well, I could do some more, but hopefully you see what I'm doing. The problem that we run into, though, is what if we have numbers that are not real standard? So instead of 70 to 90, what if I wanted to go, say, like 73 to 87, or say 74 to 86, or something like that? Well, then we would have to know more areas to do that. Well, there is a way to know more areas, and that's called using z-scores and then using a z-table. Now, to find the z-score is basically what standardizes the score. And this is how you find the z-score for a particular x value. You simply take x minus the mean and divide by the standard deviation. So if you look at our example we just did with the mean of 80 and a standard deviation of 5, then if x is 70, we can put a 70 in for x, subtract the mean, divide by 5, and we get -2, which means that that value is 2 standard deviations to the left of the mean. For 85, we can put 85 in this formula. 85 minus 80 divided by 5 is 1, so that means it's 1 standard deviation to the right. Now if you plug 80 in, you're just going to get 80 minus 80 over 5, which is 0, and of course that makes sense because 80 is 0 standard deviations from the mean. Okay, so but if we had more numbers that were atypical numbers like 67, well, we could put 67 in and find 67 minus 80 divided by 5 is -2.6. So that would mean that 67 is 2.6 standard deviations to the left of the mean. Do the same with 84 and you'll get 0.8, and you'll find that 0.8, that 84 is 0.8 standard deviations to the right of the mean. And then again for 92, you plug that in, you get 2.4. So 92 is 2.4 standard deviations to the right of the mean. So here's a couple of examples where you actually calculate z-scores. So you freeze the video and look at that, but it's just simply a matter of using this formula for the given mean, standard deviation, and the z-scores that you're given. Okay, so now the next thing I'm going to get into is reading the z-leaves. So I'll explain the process on this page, and then I'll do some examples on the next page. But let me explain one thing for you, because you might see, we're going to have to look up in a table the areas that are under a curve. And if you look in a table, you might see two things. You might see a picture like this in the table. Well, if you see a picture like that, if you look up a particular z-score, like let's say this is, z equals 1.3, well, then there'll be an area given in that table, but what that's going to give you is it's going to tell you the area from 1.3 all the way over to the left. So it'll give you this entire blue area. But whereas if you looked up 1.3 in a table that showed this picture, then that table, when you look up 1.3, is just going to give you the area from here to the mean. So in other words, these tables give you different areas. They'll do the same thing, but you got to know how to read them. So let me just give you an example. Suppose I looked up the area for a z-value using the first graph. Okay, so let's say I looked up the area for a z-value, and let's say it said this area was 0.93. Just for grins, let's say it gives you more decimals, but let's say it's 0.93. Well, if I look up the same area in this table, it's going to give me 0.43, and here's why. This table not only gives you, this table up here not only gives you this area, but it also gives you this area over here. Okay, so it also gives you this area over here. Remember, this area is 0.5 over here. So if I look up the same z-score in the table that uses this chart, then it's only going to give me the area in here, and it's not going to give me the area over there. So you have to know how to read the table in order to look up these z-scores. And let me finish with this one example. Okay, so notice, let's find the area for between the mean and a z-value of 1.45. Okay, well, this will actually give it to me. This will give me the area between the mean and 1.45. So if I look at my table, I find 1.4, and then I get over to 0.5, so that's 1.45, and I'll find the area is 0.4265. But if I look up the same value, 1.45, in a table like this, it's going to give me 0.9265, which is fine if I want the whole area. But if I just want this area here, from here over to here, if I just want that area, then I'm going to have to know to subtract 0.5 from it. I got to take off this left side away from it so that it'll give me the same number it gave me up here, 0.4265. This will make more sense in the next video when I show you some examples of finding area under a curve using these z-scores.